So welcome back. In this video we'll continue discussing map and MP inference, and now we're gonna focus on map queries. So map inference is very similar to MP. The difference here is that we're gonna work with a set of map variables that we call M, and we'll not force this set M to be the set of all variables that we have in the network. So for the MP query, the map variables must be all the variables that we had in the network, but the evidence variables. Now we will accept to be a subset of those variables. And that will make things a little bit more complicated, because in order to make inference, when we are using MPE, we could eliminate all variables by maximizing out them. But now we will have some variables that we need to eliminate by summation, that will be the hidden variables, those variables that we are not interested, is not part of our query, and it's not also part of the evidence. So those variables will need to be eliminated by summation. And the remaining values, we will eliminate them by maximizing out. So it's going to be a little bit more complicated procedure in order to make inference. But the definitions are very similar. So if you are interested in computing the map probability for the map variables M and evidence E, what we're going to have is to compute what is going to be the maximum probability for all assignments that mention the map variables into this joint marginal here that have only the marginal variables, the map variables, and the evidence E. But in most cases, we are not interested in the map probability, but in the map instantiation. That's very similar to MPE. In this case, what I'm going to do is to compute the argmax. So I'm interested in the instantiation M that has the maximum probability. Again, and similar to what we did with MPE, we do not have to work with this conditional probability here. It's going to be simpler to work with this joint marginal here. And the fact is that the instantiation that we find in the joint marginal will be the same as the instantiation that we find in the conditional probability, because we have this property here, the base conditioning, saying that the conditional probability is equal to the joint probability divided by the probability of the evidence. So, and the probability of the evidence is independent of the instantiation M, so it doesn't change anything. It's going to just change the values by a constant value, but the value, the instantiation that has the maximum probability in the joint marginal will also have the maximum probability in the conditional. So we can solve this problem also using variable elimination, pretty much like how we did with the MP. But the procedure for variable elimination using MPE was simpler, because all variables were part of the query, so we wanted to maximize all the variables that we had. Now we have some variables that we want to maximize, but other variables we want to eliminate them by summation. We can think of this process as the following. So we have, let's think about the joint distribution, and this joint distribution, it mentions the variable that are part of the map variables. There are some other variables, there are the hidden variables or the unobserved variables that I don't care about, I want to eliminate them, and there are the evidence variables. Right? So we have these three sets of variables, and what we have to do is to reduce these to a smaller marginal that only mentions the map variables and the evidence variables. And this is what I am interested in. So in this smaller marginal here, we'll have the rows, and each row has its probability associated. I will take the row that has the highest probability of all, and that is the answer to my query. This probability here is going to be the map probability. This instantiation here that mentions the map variables are the map instantiation, and that's what I'm looking for. So I will have to do this process in two steps. So first step is sum out these hidden variables, and the second step is to look for the maximum probability here, doing the process of eliminating each of the M map variables using the maximization. So we can think about this procedure as a composition of MPE and the VE algorithms. We start with the traditional variable elimination algorithm and we eliminate the hidden variables, and we conclude with the MPE algorithm where we eliminated the map variables using maximization. And also, as we had with the MPE queries, if we have just the regular factors, we will be able to answer the map probability queries. But if we want to answer the map instantiation queries, we needed to extend the factors in order to take note of the partial instantiations with maximum probabilities that we have during the elimination process of the variables using maximization. So let's take a look in the next slide, and we're gonna see the algorithm for computing map queries. So this is the map VE algorithm. So we start with a set queue of variables that we have in the network. The pi is the elimination order for the variables queue, but it's a special one because the map variables that we call M will appear last, right? So we start with the hidden variables that we want to sum out, and we end with the map variables that we will maximize out. So we're going to call S the set of factors that we have in the network already matched to the evidence. So we're going to eliminate the rows that do not match to the evidence that we set, the evidence E. And I will iterate over all variables in the elimination order in this for loop here. So we're going to start with the variables that you want to eliminate by summation, and we'll continue with the map variables. So the computation here involves first computing this sigma I factor here, that is the multiplication of all factors that mention the variable that I'm going to eliminate, pi I. If this variable that I'm going to eliminate belongs to the set of map variables, so the elimination will be a maximization, and we'll call the new factor tau I. If it's not one of the map variables, I will eliminate that variable by using a summation, and we also call this new factor tau I. And replace all the factors phi k that I have in the set S by the tau I that I just generated, and continue doing this process, one for each variable in the elimination order. When I finish that, I should have one or more factors. They're all trivial, and I will multiply those factors together in order to return the map probability to the user. So we have here a few notes. If the network is a base network, we can prune nodes and edges. So remember that when we were discussing MPE, we could not prune nodes because all nodes were or they belonged to the evidence or they belonged to the query. And but now we have also nodes that belong to the hidden variables. So we can use prune as we defined it a few lectures ago, and in this case that the node is one hidden variable, it can be pruned from the network. So the elimination order here is special in the sense that the map variables appear last, and that is going to be a problem for when we compute the width of the elimination order, because we are not free to use any elimination order that we want. We need to use this special eliminator order where the query variables, the map variables, will appear last. And the algorithm performs both types of elimination, that is maximizing out map variables and summing out no-map variables. So what is the complexity of this map VE algorithm? And in principle, it looks the same as the MPE VE algorithm, because the complexity will be n, that is the number of variables, times one exponential in the width of the elimination order. But one important detail here is that when we are working with MPE queries, we have a lot more choices for the elimination orders, so we can find better elimination orders. Now with a map, we are constrained in the elimination orders. We need the elimination orders that start with certain variables and end with other variables. So we cannot choose the variables freely as we did with the MPE. And that can be a problem in certain situations. So one example here is illustrating this figure. So we have this structure here, and let's suppose that we are free to eliminate the variables in any order that we want. So what we do is we take this structure that we have here. Let me just copy here a few nodes, right? So we create the interaction graph. So we have these connections here because we need to modelize this graph. And when we start doing the elimination, what we're going to do, we're going to eliminate this node first here. If you are free to choose where we want to eliminate first, we're going to eliminate this guy because it has a small degree. And now we're going to eliminate this one, and these two edges here disappear because we don't have the node anymore. And I'm going to eliminate this guy here and eliminate this one, and keep on doing this, right? So we have the freedom to choose the elimination order that we want. And because this is a poly tree, and because the maximum number of parents is 2 for these nodes here, they have 2 parents, we know that the tree width is going to be 2. So we can find a very simple elimination order with width 2, right? But let's suppose that we are computing a map query, and our map variables are the y1, y2, and so on. So what would happen in this case? So let's suppose that these are my map queries. So I will need to eliminate these variables last, and we'll start with x1, x2, and so on. So in this case, our interaction graph will be the following. So we have like this structure, and modelize it. So I will not be able to start with this node. I will start, for instance, with this node here. When I eliminate this node, I need to connect the neighbors. So I need to connect these two and these two here, and eliminate this node. So this node is eliminated. When I eliminate this guy here, I need to connect all the neighbors. So we need to eliminate this, connect these guys, connect these guys, connect these guys, and connect these guys, and so on. So this node is going to be eliminated. Now eliminate this guy here. Again, I have to connect this and this, and also this, and also that. Look at how many connections are doing here, right? So the width of the elimination order for the MPE query was just 2, but the elimination order for the map query is going to be n. And that means that the MPVE algorithm is going to be linear for this case, but the map VE algorithm is going to be exponential for this elimination order. So it should be clear now, but to just emphasize this result, that's very important. The problem with the map inference is the fact that we cannot choose an arbitrary elimination order. We cannot interleave variables that we are summing out with the variables that we are maximizing out. So, and the problem comes from the fact that we cannot commute maximization and summation. So we cannot change the order and do the operations in the order that we want. We needed to, in order to compute the correct result, we needed to start with summation and end with the maximization, like it is. So if you have one elimination order like pi here, we needed to start by summing out the variables x here, and let's suppose that we have 3, and we have to end by maximizing out the variables y. Let's suppose that we have 3. If we invert this order, we will not have the same results, but we're going to have an upper bound. And you may ask if this upper bound is going to be tight or not. It will all depends on this order. If this order is very similar, it tends to be very tight. For instance, if you have like x1, x2, and now we invert and put y1 and x3 and y2 and y3, this upper bound tends to be very tight. But if we choose a different order where we completely invert things like y1, y2, y3, x1, x2, x3, so these upper bounds tend to be very loose. Okay, and now that we know that not every elimination order will going to be useful to us, we can define what's going to be the elimination orders that give the correct results. So I'm going to call one elimination order pi as m constrained if the variables, the map variables, appear last in the elimination order pi. And because only these m constrained elimination orders will give us the right results, we can also compute what is going to be the tree width of a certain network according to this m constrained elimination order. So we call the m constrained tree width of a graph the width of the best m constrained order. So we can conclude that computing those map queries are more difficult than computing the MPE queries in this context of a variable elimination algorithm. So let's use one example to check our understanding of how to compute the map instantiations. So it's the same example that we had before, but now we're going to compute the map query. So going to be the map probability. We have evidence A equal yes, and the map variables are S and C. So in order to the elimination order to be m constrained, to be the correct one, S and C must appear last in the elimination order. So exactly as we did here. So we have all those tables that are going to multiply together. We're going to follow this elimination order pi. So start with A, T1, T2, and S and C. So here we have the iteration graph, the model graph, and also we are changing the notation and using this factor notation, phi 1, phi 2, until phi 5. So we start this inference process by taking note of the evidence. So we have evidence that is A equal yes. So what's going to do is to eliminate the rows that do not match the evidence. So they have A equal no, and that's gonna happen in the next slide. All right, now we have this factor here. The phi 5 only mentions the little a, that is the A equal true. Okay, so now we started with the elimination process. We're going to start eliminating the variable A, and this is going to be a very simple elimination because we have already set evidence, so we have only A equal yes, and we'll continue to T1 and T2. For these three variables, we do the elimination by summing out the variables, and when we finish with just one small marginal over the variables S and C, we're going to move out to the elimination of these two variables by using the maximization procedure. So this is the elimination of a variable A. It's very simple because actually A has been already eliminated from this because we have only the constant here, so we don't have the variable anymore. So we eliminate A, and we have this new factor that is tau 1. Now I'm going to move on, eliminated the variable T1, and we take all the factors that mention T1. We have the factor tau 1 and also the factor phi 2. We're going to multiply these factors together, and now we have a larger factor that mentions three variables, T1, T2, and C. So I'm going to take this new factor sigma 2 that we just created. This is the only factor that mentions T1, and we can eliminate the variable T1 by using the process of summation. So if we look here, we have the summation. Because we have the summations with non-zero values with zero values here, it will be the same thing as maximizing the computation, but believe me, I'm doing here is the summation. So we eliminated the rows, and now we have a new factor that we are calling it tau 2 that only mentions the variables T2 and C. So no other factor going to mention T1 anymore. We're going to continue with the elimination of T2, the next variable. So in order to eliminate the T2, we have to multiply the factors that mention it. So we have this new factor tau 2 that mentions the variable T2. You also have this factor here that originally in the network, the phi 4, that also mentioned T2. So we have to multiply these two factors and create a new factor. So this new factor, we'll call it a sigma 3, mentions T2, S, and C. And now we're going to eliminate this factor by summation. Now it's going to be the last factor that we eliminated by summation, and the next ones we're going to eliminate it by maximizing out. So the elimination by summation, we know how it works. We are eliminating the variable t2. So we take the matching assignments here, and we sum them. So we have 0.64 and 0.04. So we see now we have 0.68. We're going to sum these two, also 0.68. We're going to sum these two, 0.77, and sum these two, 0.77. Now we eliminated T2. We don't have any other factors mentioned in T2. We're going to continue now to eliminate S and C. So we're going to multiply all the factors that mention S. So we have this top 3 that we created, and the one original factor that was that is phi 3 that also mentions S. We're going to multiply this factor together, and now we have the sigma 4 factor that mentions C and S. And we have one more factor that mentions S, that is the phi 1. So we need to multiply this factor as well. So the sigma 4 we just created, multiplied by the phi 1, we have this sigma 5 here, and now I'm in position to eliminate the variable S, and we're going to do this by maximization. So now I'm going to eliminate the variable S by maximization. So S is going to be eliminated, so we take the matching assignments of C. We look at to see which one is the largest, so we compare this 0.18 with the 0.004. The maximum one is 0.018, and we also will take note of the assignment that came with this probability, and the assignment is this male here, and a copy here. Remember that when we are doing this for the MPE, we have these very long assignments because every variable that was not evidence was part of the query. But now, because only S and C are part of the query, are the map variables, I will have a smaller assignment just for these two variables. And we're also going to compare this guy here with this guy. This is the largest one, so we copy it here, and also the male, that is the assignment for the sex, is going to be here, right? So we're going to move on and eliminate the last variable, that is C. So this is the elimination of C. We have just one factor that mentions C, and it is the tau 5 that we just created. So we just compare these two values here, take the largest one, that's 0.351, and bring the instantiation of C here. So this is the answer for our query. So this is the map assignment for S and C. So it's going to be male and no, and that's going to be the probability. And this is the probability of S, C, and E. So basically here, the information that I have here is the map probability for S, C, and E. If you want to compute the conditional probability, we need to divide this guy here by the probability of E. So we need to know what's going to be the probability of A equal, yes? I computed this guy here, and it's 0.7205. So what I'm going to do is to divide this 0.351 by 0.7205, and that's going to be around 49%. Right? And that is the answer to my conditional probability. Okay, so we got to the end of this lecture, and we discussed MEP and map queries, and we saw a new algorithm that is basically a variation of the variable elimination algorithm that introduces a new operation that is elimination of variable using maximization. One interesting detail here is that the MP queries only use multiplication and maximization operations, and the map queries, they need an extra operation that is summing out the variables. But in the case of MPE, that only relies on multiplication and maximizations, we can easily work with log probabilities. In this case, the multiplication becomes a summation, and the maximization continues to be a maximization because larger probabilities lead to larger log probabilities. That is not the case for MAP because mapping requires sum out variables. In this case, that's complicated to work with log probabilities because we do not have a natural operation for sum out log probabilities. If we want to work with log probabilities in map queries, we would be required to transform the log probabilities into probabilities in order to sum out the variables. But in this case, we lose the property of these algorithms to become more numerically stable, right? Because as we transform the probabilities into log probabilities, we can transform very small numbers in large negative numbers. And in this case, it is less likely that we will incur in numerical underflows. All right, so this is a shorter video. We only focused on the variable elimination algorithm for MP and map queries, and these two algorithms are discussed in the book. We can look at the chapter 10. But because we are only focusing on the variable elimination algorithm, we're going to see that you don't have to read sections 2.2, 2.3, 3.2, and 3.3, because these sections, they discuss all the algorithms. Basically, these algorithms are based on systematic search. They are very interesting algorithms, but in order to keep this material short, we will not go over these algorithms for map and MPV. All right, that's all for this lecture, and I see you in the next video.